let us look at this sum first. Okay, we have already done the work when f is the omega function. In general, what happens when you have an additive function? So note, summation n going up to x, f of n, what is this equal to? Summation n up to x, summation p raised to the some, let me call this nu, okay, it double divides or double bar of n f of p raised to the nu. Okay, and when you interchange it, what do? I have to first take all possible prime powers up to x. Okay, so what we do is take first of all possible prime powers up to x. Okay, f of p to the k, and then in the inner sum consider all those n up to x, so that k is the highest power of your prime dividing that number. So let me write this down as, so let us denote, okay, let me actually do this. For each prime p, let nu of n comma p, let this number denote the highest power of p such that p raised to the nu of n comma p divides n. Okay, this notation here we have to be clear about which prime we are talking about. So now we can write the above sum as, first of all, go over all possible prime powers up to x, take f of p raised to the k, okay, and the inner sum is over all those n up to x for which k is equal to nu of n comma p. Do you see this interchange of summation? We are taking out all possible prime powers, and then in the inner sum, given any particular prime power k, we are counting all those n for which p to the k is the highest power, dividing the number n. All right. Now, this inner sum is something that we also discussed a few minutes ago. So let's keep this as p raised to the k less than or equal to x. So what does this mean? When you say k is equal to the highest power, what does that mean? You are running over all the n up to x for which p raised to the k divides n, but p raised to the k plus 1 does not divide n, right? And this can be written as the sum, of course, there is an f of p to the k. So f of p to the k, and then in the inner sum, what do you have? First, you run over all those n less than or equal to x, for which p raised to the k divides n 1. But you have to remove all those n's which are multiples of p to the k plus 1. So, you have to take away all those n's which are multiples of p to the k plus 1. By now, you know what this quantity is. This is just summation p raised to the k less than or equal to x f of p raised to the k times, what should you have here? You will end up getting greatest integer minus x over p raised to the k plus 1. Okay, now I want to make two observations. So far we have an absolute equality. What we do now is we give upper bounds as well as a lower bound for this. Okay, so observe that this inner thing is certainly bounded above by x over p to the k. Okay, so what we see is that summation n less than or equal to x f of n is certainly less than or equal to x times summation p raised to the k less than or equal to x f of p to the k over p to the k. This is the first inequality that we are going to keep in mind. To have a lower bound, it's a little more subtle. So, suppose you have any real number a. Okay, let's take any positive real number a. You can write this as the greatest integer plus a fractional part. What do you know about the fractional part? The fractional part has to be strictly less than 1 and some positive number. Okay. Then similarly, so suppose you have so now suppose I take the difference. So a minus b is the difference of their greatest integers minus fractional part of a minus fractional part of b. Okay. So, in other words, your box A minus box B is equal to A minus B plus the corresponding differences of their fractional parts. So far so good. Now, A, fractional part of A lies between 0 and 1, fractional part, negative of fractional part of B lies between minus 1 and 0. So, what can you say about fractional part of A minus fractional part of B? This would be greater than minus 1 and strictly less than 1. Okay. So, at any rate, this is certainly greater than A minus B minus 1. Plus, okay. Yes, that's fine. And then therefore, so box of A minus box of B would be A minus B minus fractional part of A minus fractional part of B. Okay. And because now you can from this you can, using properties of fractional parts, because of the fact that the fractional part lies between 0 and 1, so its negative lies between -1 and 0, you will end up getting that this is strictly greater than a minus b minus 1. Okay? So, because of this, I am going to leave this intact and just work on this side. Because of this, the other inequality that we get is that thus summation n less than or equal to x f of n is greater than summation p raised to the k up to x f of p to the k over p to the k times 1 minus 1 by p, okay, coming from x over p to the k minus x over p to the k plus 1 minus so into 1 over p raised to the k minus, okay, this is not the greatest integer, it's just the parenthesis. Should be careful with the notations. Okay, and therefore this is, what is this thing equal to? This is p to the k greater than or equal to x f of p raised to the k over p to the k times 1 minus 1 by p, okay, minus summation p to the k less than or equal to x f of p raised to the k. Are you convinced with this inequality? This is E of x, right? So, the other inequality that we have just derived is that summation n up to x f of n is greater than or equal to E of x minus, actually this is a strict inequality, p to the k up to x this is also something that we will use. Okay, so we've got these two, we have an upper bound here and we have a lower bound as well. So, we are going to use that. Notice over here you have a negative of 2. We are trying to derive an upper bound. So, this is less than or equal to. You leave these intact for now, we will come to them again. So, 1 over x n up to x f square of n plus E of x whole square minus 2e of x over x times this. Now, we have a lower bound for this summation f of n, but then there is a negative here. So, that will become, so negative of, so this will be less than or equal to negative of 2e of x over x times the term E of x minus summation pk less than or equal to x f of p raised to the k. This is the x I was missing out, right? So, then there should be an x here also. This is what you are saying, right? Okay, thank you. Thanks for pointing this out. and in fact this is actually important. So, negative of this would be less than negative of x times e of x plus this term here. So, we can put this here. So, you have to, okay, yeah, this is correct. Okay, so what you end up having here is, so actually, yes, you need to have, yeah, this is correct. So, you will have minus 2 e of x whole square, okay, plus 2 e of x over x summation p raised to the k less than or equal to x f of p to the k. Okay, and this is of course e of x whole square, okay, and then f square of n plus e of x whole square minus. So, there is a slight problem with the alignment, but I think you know where we are going. Now, e of x square minus 2 e of x square is just minus e of x square, all right. Now, let us look at this term here. Let us look at the only term that remains. So, 1 by x summation n less than or equal to x f square of n. Okay. So, what do we have here? This is equal to 1 over x summation n less than or equal to x f of n times f of n. So, you have first summation over all the primes dividing n f of p raised to the mu of n comma p, okay, and then you are also multiplying this by, now let's index the primes by q here, f of q raised to the mu of n comma q. So, you have two different sums inside this sum which you are multiplying. So, you write a term by term product. Okay, so all possible. So, first, so all possible primes p and q such that p divides n, q divides n, f of p raised to the mu n comma p, f of q raised to the nu of n comma q. So, what will you do now? How will you interchange? So, first we note, so let us take two cases. First, when you could have, when you take the sum, you could have primes which are equal to each other. So, take that case first when p is equal to q, and then take the case when p is not equal to q. Okay. So, 1 by x n less than or equal to x. Okay. So, sum over all the prime divisors of n and square of p raised to the nu of n comma p whole square. Okay. And the other term is more interesting. So, 1 by x summation n up to x. Okay. So, p not equal to q, we have f of p raised to the mu np times f of q raised to the mu nq. Okay. Now, let us look at the second part carefully. What is going on here? If you do an interchange for the second sum, okay, so this is just for the first thing, we don't have to worry so much. So let's look at the second bit. So 1 over x. Okay, now what we do is take all possible p to the k and all possible q to the l, so that both p to the l and q to the l divide n. Okay. Now, if p to the k divides n and q to the l divides n, their product also has to divide n if these are distinct primes. Okay. So now what we do is, for the second term, so this part is just all possible pairs of primes which are not equal to each other, such that p to the k times q to the l is less than or equal to x, f of p to the k times f of q raised to the l, okay, times what is the inner sum? The inner sum runs over all those n's up till x, such that mu of n comma p is exactly equal to k, and mu of n comma q is exactly equal to l. Okay. What is this inner sum now? So 1 by x, the outer sum is over all those p and q, so that, and all corresponding powers, so that the product is less than or equal to x, f of p to the k times f of q to the l. Okay. Now, to say that mu of n comma p is equal to k is to say that p to the k divides n, but p to the k plus 1 does not divide n. And similarly for q to the l. Q to the l divides n, but q to the l plus 1 does not divide n. So, you want p to the k to divide n, q to the l to divide n, therefore, their product must divide n. Okay. So, what are the possible multiples of p to the k times q to the l, which would be less than or equal to x? That will just be the greatest integer, x over p to the k times q to the l. But you have to take away those multiples, those numbers which are multiples of p to the k plus 1 times q to the l. So, you have to remove box x, greatest integer, x over p raised to the k plus 1 q to the l. Similarly, you also have to remove all possible multiples of p to the k times q to the l plus 1 minus x over p to the k times q to the l plus 1, but then you may have taken away some terms twice. Which are those terms? Those terms which are multiples of p to the k plus 1 times q to the l plus 1. You have ended up removing them 2 times. So, you need to put them back. So, there is this inclusion exclusion going on here. So, box of x over p to the k plus 1 q raised to the l plus 1. Okay. Okay. Now, again, using the fact that you can write this as, so greatest integer of a can be written as a minus its fractional part, where the fractional part is suitably bounded. Okay. So, there are 2 terms with negative and 2 of them with positive, and taking all possibilities, what you will end up getting is that this is bounded above by, I will let you verify that bit, 1 by x summation p not equal to q, p raised to the k, q raised to the l less than or equal to x, f of p to the k times f of q to the l over p to the k, there's no over, it's just f of p to the k times f of q to the l times x, I have to be careful this time, I will not forget the x times x over p to the k times q to the l into 1 minus 1 by p into 1 minus 1 by q, okay, plus 2. That plus 2 is the upper bound coming from the fractional parts, okay. So, combining this term here and what you obtained for this, you can write this out as follows. So first you have here what is going on here. So again you can take f square of p to the k outside, okay, and then count all those n's up to x such that p to the k, such that k is exactly equal to nu of n comma p. So what you end up getting here for the first part is, so combining this and what you did for the second part, you have the following inequality. First is 1 over x times, when you do a suitable interchange, what you end up getting is summation p raised to the k less than or equal to x f of p raised to the k whole square times x over p raised to the k, okay. And so here you are using actually the upper bound idea, right. I am just saying that this thing is less than or equal to this. Okay, then you have the next part, which is plus 1 by x. In fact, let me just, since it's, write this here. Plus 1 over x into all possible p not equal to q, for which p to the k, q to the l is less than or equal to x, f of p raised to the k times f of q raised to the l, let's not forget the x, okay, over p to the k times q to the l, okay, plus 2 over x, again the same sum over p and q as above, but this time you have 2 times 2 over x times f of p to the k times f of q to the l. Okay, there is no x coming in the numerator here. Okay, now what we observe is, if you look at each of these terms, what do you know about the first term? So x and x will cancel away, right? So this is summation p raised to the k less than or equal to x, f of p to the k whole square over p to the k. Okay, recall this is just the square of d of x. Okay, what about the next one? Again, your x and x will cancel away. What you have is, oh, I missed again. I missed 1 minus 1 by p into 1 minus 1 by q. Okay, there would be a 1 minus 1 by p. No, here we are just taking upper bound, so we are fine. Now, notice what is this. Suppose I were to take summation of f of p to the k times 1 minus 1 by p over p to the k and square that sum. Then every term here, okay, this will get cancelled away. Every term here will appear in that product. But that product itself, you know, this is, so all I'm saying is that the second term is less than or equal to summation p times f of p raised to the k over p raised to the k, okay, into 1 minus 1 by p whole square, assuming that your f is a non-negative function. Okay, if f is a non-negative function, to this term, to this sum, you can add a bunch of other non-negative terms in order to get this whole square. Okay, and the last one we just leave 2 over x summation p not equal to q such that p to the k q raised to the l is less than or equal to x f of p to the k times f of q raised to the l. Okay, so assuming, let us assume, later we will generalize it to those functions which could take negative values as well. To begin with, assume that f goes from, it's an arithmetic function taking non-negative real values. So in that case, this whole thing, using what we showed above, is less than or equal to, the first term here is just square of d of x the second term is just the square of e of x then you already have e of x square, then you have minus 2 e of x whole square plus 2 e of x over x summation p raised to the k less than or equal to x f of p raised to the k. Okay, but there is also something left over from here, namely the last bit. So we write that also. So plus 2 over x times summation over all possible primes p and q with these conditions, f of p to the k times f of q raised to the l. Okay, p not equal to q and p to the k, q raised to the l is less than or equal to x. So to summarize, we were looking at the different pieces of the variance term that we want to estimate, and we are now going to put it all together. So this gives us, to conclude, thus 1 over x is less than or equal to d of x whole square, okay, then e of x square and minus 2 e of x square get cancelled, plus 2 e of x over x times summation p to the k less than or equal to x f of p raised to the k plus 2 by x times summation p not equal to q but p to the k q to the l less than or equal to x of, what is the term that you have, f of p to the k f of q raised to the l. So there was nothing too complicated. It's just you have to carefully record all the different pieces and put them together without making an error. Okay. Now note the following. So what do we do with these? So your e of x. So remember, what are we going towards? We are trying to show that this whole thing is less than or equal to some epsilon times square of d of x. So now we have to relate these to our d of x, and this is where another very nice technique, namely the Cauchy-Schwarz inequality, comes into the picture. So this is what we now do. Okay, so basically to finish the proof of Turan-Kubilius inequality, we have to do two more things. We have to apply Cauchy-Schwarz inequality to these terms here, so that this whole thing you will be able to write as less than or equal to some 2 plus epsilon prime of x times square of d of x. But remember, here we had made a fundamental assumption that your f is taking non-negative values. Then we have to extend, we don't have to do the whole thing again, but from this we have to observe how to generalize to any function which can also take negative values. So these are the two main things. You again also have to generalize to complex valued functions, but that is also trivial. Okay, so I'll just talk about real valued functions today, and in the notes, of course, a discussion of complex valued functions is also given. So let us look at these term by term. So let us take this sum. P raised to the k less than or equal to x f of p to the k. Okay, so this is, here we are actually using some arithmetic manipulations and some of the standard inequalities that we use a lot in analytic number theory. So here let's write this as, so this is equal to p raised to the k less than or equal to x f of p to the k over p raised to the k by 2, okay, and times p raised to the k by 2. Let this be one term, let this be the other term, and let us apply Cauchy-Schwarz inequality. So this will be less than or equal to summation p to the k less than or equal to x square of this over p to the k and the whole thing raised to the half times summation p raised to the k less than or equal to x, again square of p raised to the k by 2, which is p to the k raised to the half. What is this? This is just your d of x, isn't it? So this is just d of x times summation p raised to the k less than or equal to x, p raised to the k raised to the half. This part does not depend on f at all. So, it is only d of x that depends on f. The second sum does not depend on f at all. Okay. Okay. Now, let us take the following term. Let us take this term here. So, now you have summation f of p to the k, f of q raised to the L. So, again what we do is we write this as p raised to the k by 2, okay, times q raised to the L over 2 and multiply by p raised to the k by 2, q raised to the L by 2. Again apply the Cauchy-Schwarz inequality. So, what do you have? This is less than or equal to summation f of p to the k, f of q to the L whole square over p to the k, q to the L raised to the half, and then you have the other term summation p, summation over appropriate pairs of primes p and q, p raised to the k, q raised to the L, the whole thing raised to the half. Now, notice this thing here, the inner sum, without the half exponent outside. If you just look at the inner sum itself, it seems to be a product of d of x whole square with itself. So, this will be d of x, the inner thing here will just be d of x raised to the power 4, right, because d of x was the square root of something. And so, what you end up getting is, so this is just less than or equal to d of x whole square times something which again does not depend on f at all. Okay. Similarly, now, so what do we have? We have d of x whole square plus 2e of x over x times this, which we have estimated here in terms of d of x. Now, we make another observation. What is e of x itself? E of x, so by definition, it is p raised to the k less than or equal to x, f of p raised to the k over p raised to the k times 1 minus 1 by p, right? 1 minus 1 by p is less than or equal to 1. So, clearly this is less than or equal to summation f of p to the k over p to the k, right? Now, again we can apply the Cauchy-Schwarz inequality. So, what we do is, so first what we do is we write this as summation p to the k less than or equal to x, f of p to the k over p to the k times, sorry, p to the k by 2 times 1 over p raised to the k by 2. Treat these as the two different sequences and apply Cauchy-Schwarz to them. So, this is less than or equal to summation p raised to the k less than or equal to x, f of p to the k whole square over p to the k, right, and the whole thing raised to the half and then the other one is again p to the k less than or equal to x 1 over p to the k raised to the half. Again, this is just d of x. So, putting all these to the terms here, what do we get? First is just d of x whole square. The next one is plus 2 by x. E of x, you told me, is less than or equal to d of x times something that does not depend on f this half is vital. So, 2 by x times this times you have this sum here, for which again you have written an upper bound in terms of d of x times summation p raised to the k less than or equal to x p to the k raised to the half. This takes care of the second term. Then you have the third term here. So, you have plus 2 by x, and this term you have shown is bounded above by d of x whole square times again a part that does not depend on f. All right. So, clubbing everything together, now we are just like a step or two away from the main inequality that we want. So, this tells us that the variance term one by x summation n up to x f of n minus e of x whole square, this is less than or equal to, since d of x whole square is common everywhere, so we take that out. What are we left with? 1 plus 2 over x times summation p raised to the k less than or equal to x 1 by p to the k half into summation, another summation over all the prime powers up to x with p to the k in the numerator half, okay, plus finally you are left with 2 by x, d of x whole square has gone out and you are just with all the p's and q's, so that p to the k q to the l is less than or equal to x, p to the k q to the l raised to the half. Right? Now, this part 2 by x into this plus 2 by x into this. With the knowledge of the average order of the von Mangold functions, the behavior, the sums that you have studied, you can actually show that this part, this sum of these two will be a function of x which goes to 0 as x goes to infinity. Okay? I am going to give this as an exercise in your next assignment. So, this can be shown to be d of x whole square times 1 plus some function epsilon prime of x, which by the way would be less than, you have a really nice bound for it, log x over log x. Clearly, this is going to 0 as x goes to infinity. This I am not going to prove it in the class. It will be given to you in the exercise. Maybe we can discuss this in the live session. So, what have you done? You have shown that if f is a non-negative function, then this sum is less than or equal to square of d of x times 1 plus something which is going to 0 as x goes to infinity. Okay, so we have actually proved the Turan-Kubilius inequality for non-negative functions.